Now we want to look at the issue of parallel circuits. Okay? So, parallel are when you have more than one loop. Okay? And one way to think about this is imagine if I have a battery that looks like this. And this is the plus terminal, this is the minus terminal. And I have a resistor out here. Or let's use a light bulb as a physical example, right? So I have a light bulb hanging out here. And so what I would do is I would connect the positive terminal and the negative terminal like this, and hopefully my light bulb would then light up, right? What if I want to add a second light bulb? Okay, I can do that two ways. I can either add my light bulb like this, where my light bulbs are connected in series. So this is a series light bulb circuit. Or, and if my light bulbs are identical, they'll have the same brightness, but they won't be as bright as the one up top. Or another way would be to simply connect this second light bulb to the terminals independently of the first light bulb. And so now both light bulbs are feeling the total voltage of the battery, whatever the battery's voltage is. Okay? Whatever the battery's voltage is, you would be or the light bulbs would be experiencing. Okay? So this is what's known as a parallel circuit. But notice you have two loops. In one case, I have current running through this light bulb like this. And in the second case, I have current running through this light bulb like this. So I have two separate loops, whereas in the series case, I have one. Now, why would I connect a series of light bulbs in this fashion? Well, suppose one of the light bulbs burns out here. If one of the light bulbs burns out and we no longer have that light bulb lit up, right? What happens in that case is the path is now broken because the filaments are burnt up. There's no complete path for the light bulb or the current to flow, and without a complete path, both light bulbs are not lit. So neither light bulb is lit. But when you connect things in parallel, because each light bulb has its own independent path, then even if one burns up or shorts out, the other one stays lit. Okay? So it turns out that there are situations where the parallel case is more convenient. Okay? And so the parallel situation is well worth the investigation. Now, it turns out old strands of Christmas lights. I won't spell out the whole word Christmas. Old Xmas lights were in series. And when a bulb in those old strands burnt out, you had to test the whole strand. You had to test each individual bulb one by one to find the one that was burnt up. But modern strands are built on this principle, so you can easily identify the ones that are burnt out and they don't affect the rest of the strand. So modern Xmas strands are built like this. Also, your home is built more on the parallel case in terms of your appliances. And this is so that if instead of light bulbs, if I have appliances like a fridge and a stove, if your stove shorted out and quit working, then if things were connected in series with your breaker box, then your fridge would go out too, and your food would get spoiled very, very quickly. Whereas if you have things wired in parallel, if this is a fridge, and this is your stove, if your stove shorts out, your fridge keeps working and you don't have to worry about your food spoiling. So there are advantages to this system. Now, when we draw this schematically, right, we typically draw it like this. So here we have our battery, here we have our first resistor, we'll call this R1. But remember what we argued before. Each point, if I were to measure the voltage at each point across these branches, I would measure the same voltage that I measured across the battery at each of these points. Okay? And so if I put wires here and then build my second resistor like this, then this is equivalent to hooking both resistors directly to the terminals. Okay, so this is a one of the basic ways we denote parallel circuits schematically. Okay, sometimes you might see this turned on its side, but very often you'll see it like this. And notice we have the same two loops, right? So we have the first loop that goes through here, and we have the second loop where it goes through here. Now technically, okay, and we'll see this when we get to Kirchhoff's rules, technically there's a third loop which I could analyze current flowing through just the loop that contains the resistors. Okay, and that would be the loop where the light bulbs kind of bypass the battery and are just considered to be connected to each other. But from an initial analysis standpoint, we usually don't use that loop. But there technically are three loops here, just to be very clear. And so we label this R2. Now, remember that in the parallel case, both resistors experience the voltage of the battery. Okay, so the voltage across the first resistor and the voltage across the second resistor all equal the voltage of the battery. So they don't add up in this case. It's not a case of the voltage across V1 adding up with the voltage across V2 to make the voltage of the battery. It's that all of the voltages are the same, because this point and this point have the same plus and minus value that the battery does, and so when I connect the second resistor to those points, it's equivalent to hooking it across the battery directly. But what is not the same, and let me actually redraw this at this point because it got fairly busy fairly quickly. When I have the battery, right? Once again, all the battery knows is that there is a total resistance out there in space that it experiences. And from the battery's perspective, Ohm's law still applies. Okay, but the total current here is just going to be the current that the battery sees going out and that the battery sees coming in. Okay? But each individual resistor has its own current that it is drawing from the battery. And when you see it in this kind of picture, you can kind of see what's happening. The green and the red, when they meet this junction right here, the green and the red add up to make the purple. And here, when the current leaves the battery, the purple is the combination of the green and the red, and then they split right here. So anytime you have a junction, what you'll have is currents splitting off. Anytime you have a junction where currents can pick their direction, the currents will diverge, right? And so you have a total amount of current entering this junction, which is just I total. I total hits this junction, and then it splits between the red and the green, or between I1 and I2. So I total splits into I1 and I2, and then at this junction, they add back up to create the total once again that the battery experiences. So in this case, in the parallel case, the currents add. In the series case, it was the voltages that add, and the current was the same everywhere. But in the parallel case, it's the voltages that are the same between all of the elements, and the currents add. Okay? And so once again, to get a formula for how the parallel case works, to get a formula for the total resistance in relation to each individual resistor, we will use this property in combination with the fact that the voltages are the same everywhere. So I total is the current that the battery sees when we apply Ohm's law to the battery. Okay? And I total is equal to the battery voltage divided by the total resistance, whatever that turns out to be. Okay? But once again, Ohm's law applies to each individual circuit element, so that the current through here and the current through here will obey Ohm's law such that I1 is equal to V1 over R1, and I2 is equal to V2 over R2. And so if I insert this expression for I total, and then this expression for I1, and this expression for I2, I get V battery over R total is equal to V1 over R1 plus V2 over R2. But because the voltages are equal everywhere, they cancel out, and I'm left with the formula 1 over R total is equal to 1 over R1 plus 1 over R2. And if you had multiple resistors in here, it would just continue in this pattern. Okay. So this is the general formula when you have resistors in parallel. They add reciprocally. Okay. They add as their reciprocals. Now, in the special case, okay, in the two resistor special case, we have 1 over R total is equal to 1 over R1 plus 1 over R2. And so this is the total equivalent resistance that your battery sees when you have two resistors in this configuration. Okay? So when you have your resistors in this configuration, what you can do to actually calculate the total resistance is get common denominators, and so then you would have R2 over 1 R2, and then plus R1 over R1 R2. And then you can add these up, and because it's addition, it doesn't matter what order you add them in, so I can just say R1 plus R2 over the product of R1 R2. And now I can take the reciprocal of both sides. So the total resistance that the battery experiences, okay, is just the product of your resistors divided by their sum. So for example, if we had resistors of 6 ohms each, just for example, then 6 ohms times 6 ohms divided by 6 plus 6 ohms. Ohms cancels with ohms. And I get 36 ohms divided by 12. And that turns out to be 3. So this circuit, as far as my battery is concerned, and the amount of current that the battery will push, is equivalent to this circuit, where the equivalent resistance is 3 ohms. Okay, so what that means is the total resistance in a parallel circuit goes down. Okay, the total resistance is less than the smallest resistor. your total resistance is going to be less than your smallest resistor. And that is one of the special features of the parallel case. And this is general. Now, special cases. Okay? Special cases are one, when your resistors are equal. In that case, what we just saw, your total resistance is going to be R1, R2, divided by R1 plus R2. And if they're equal, then I can drop my subscripts, and this is just the same thing as R times R, which is R squared, over 2R. And one of the R's up top cancels with the R there, and my resistance is cut in half. When you have equivalent resistors, your equivalent resistance, or your total resistance that the battery experiences, is just half of that value. And that's what we saw here. When I had 6 and 6, the total resistance was just 3. In the second case, what happens if R1 is much larger than R2? So, for example, like if I had, say, 1 million ohms, and this was 10 ohms, right? What would happen in that case? So in the extreme where one is far more or far larger than the other one in terms of its resistance, then our total would do this. Well, in the case that R1 is much larger than R2, then the sum R1 plus R2 is just going to approximately be R1. If I have 1 million ohms in one resistor and I add 10 ohms to it, it doesn't really add all that much. It's far less than 1%, right? So this is approximately going to be R1 times R2 over R1. And R1 cancels out, and I'm left with R2. My equivalent resistance is very close, very approximately equal to the value of the smaller resistor. Here's why. You've probably heard the statement that current takes the path of least resistance. This is not quite true. Current doesn't take the path of least resistance. Current prefers the path of least resistance. So if I have, for example, say like a 12 volt battery, and I have a 10 ohm resistor, and that's in parallel with a 1 million ohm resistor, okay? Then let's consider what happens. Remember, if we think about each of these producing their own current, okay? So I look at the current produced by just the 10 ohm resistor. I look at I1. I1 is going to be 12 volts divided by 10 ohms, or 1.2 amps. I2, because this resistor feels the exact same voltage, it will produce a current consistent with Ohm's law, and its value will be 12 volts divided by 1 million ohms. And 12 volts divided by a million, 12 divided by a million is, if we punch this into our calculator, this is going to be 1.2 times 10 to the negative fifth amps. Okay? So remember that I total is, this is not going to be approximately, this is going to be exact. I total is the sum of I1 plus I2. But this is going to be approximately just equal to I1 because 1.2 is so much bigger than 1.2 times 10 to the negative fifth, right? It would be measurable by our standards. You could actually measure this if you have a sensitive enough ammeter, but in terms of how large this is compared to this, it's very negligible under most circumstances. And so your total current is just more or less going to be I1. And so, because of that fact, when I calculate what the resistance ought to be, just based on those considerations, the total current, if I divide the voltage of the battery divided by the total current, this is going to be 12 volts divided by approximately 1.2 amps, which gives me 10 ohms. So what this is telling you is that when the you can think of it this way conceptually. The current leaves the battery in a total form or a total amount, and when it hits this junction, it splits into I2 and I1. But they split themselves based on the resistance that they see. The current will split itself based on the resistance that it sees. 10 ohms is much less resistance than 1 million ohms, so more of the current will be able to flow through this path. 1 million ohms is a lot of resistance comparatively, so very little of the current is going to be able to move through that path. It still will move through that path. So it's not that current takes the path of least resistance, but it's that the current prefers the path of least resistance. Okay. So these are your two special cases. When you have your resistors are equal to each other, the total resistance will just be half of the value of either individual resistor. And when one resistor is much larger than the other resistor, that larger resistor doesn't draw very much current, so most of the current is forced through the smaller resistor, and hence the battery thinks that the equivalent resistance is just the value of the smaller resistor. Okay, but that's when you have a large gap between your two resistors. One of your resistors is several times or several factors larger than your other one. So, as I said, the total resistance is always going to be less than the smallest resistor. What happens in non-extreme cases? So what happens if I have, say, R1 is equal to 20 ohms and R2 is equal to, say, 100 ohms? Okay. How much smaller than 20 will you be? Well, the smallest I can get, right? The smallest equivalent resistance that I can get if one of my resistors, or at least if the smallest of my resistors is 20, then the smallest I can get is 10. Because if my other resistor is 20, then the total resistance will be 1/2. but the largest resistance I can get is approximately equal to the smallest resistor as well. So our total range is going to be restricted to between half of your smallest resistor and the value of your smallest resistor. So your total range for your values in parallel cases will go between half of your smallest resistance, if your resistors are equal, up to the value of your smallest resistor if there's a large gap. But when you don't have a terribly large gap, what happens? So my total resistance in this case, the product of my resistors divided by their sum, and this will be 20 times 100 divided by 120. And this is ohms squared, and this is ohms, and so one of those cancels. And when I do this, the larger the gap, the closer the value will be to your smaller resistor. So we would actually expect this to be somewhat close to 20. It might be like 17 or 18, right? So if I take 20 times 100 and I divide that by 120, we get 16.67. Technically it's 16.6 repeating, so 16.67 if you want. And so when you have non-extreme values, you just have to calculate this out, right? But then everything that we saw from the series case applies. So Ohm's law applies to the total circuit and each element. So you'll have the value of the battery is equal to the total current times the total resistance. You'll have V1 is equal to I1 times R1, and again the voltages are equal, and the voltage will also be equal for the second resistor, but that will equal I2 and R2. Okay? And then you can also calculate the powers. Once you have applied Ohm's law and you know everything about each resistor, you can then also get the powers. And you can show that the power of the battery is equal to the power of each individual resistor summed up. Okay? But there's something to note, okay? In the series case, the resistor with the higher value drew more power, right? It dissipated more power. In the parallel case, the resistor generally with the smaller value will dissipate more power. And this is because it's drawing more current. Okay? The value of the resistor with the smallest value will draw the larger current, and because it draws the larger current, both of them are connected to the same voltage source, so both of these voltages are the same. So if one of the currents is larger than the other current, then that power will be larger than the other power. So in the series case, the resistor with the larger value will dissipate more power. In the parallel case, the resistor with the smaller value will dissipate more power. Okay? So that is a bit about parallel. And the next video will talk about Kirchhoff's rules.